Let's talk now about properties of alcohols. And this topic has to do a lot with intermolecular forces. So let's think of a series, and we're going to organize those in, say, increasing boiling point, as increasing boiling point. So say that I have butane, and now I have chlorobutane, and now I have butanol. So here, what do we do about predicting in a series like that what is the order of boiling point, say increasing boiling point? So here, what you need to do is analyze what type of intermolecular forces are present in any of these molecules. So let's say, in the case of butane, the forces that you have intermolecular forces are London dispersion forces, also called van der Waals, which is just fleeting dipoles like that. That force is not very strong, so we're predicting that is a low boiling point. Now, if we have that compound, now we have a dipole, and because we know that this bond is polar, that it will be delta negative here and delta positive here at the carbon. So, and dipole forces are stronger. Dipole, and molecules would be organized the following ways. Let's say this is a dipole, so you will have a number of interactions like that. And remember that the stronger the interactions that between molecules, you need to put more energy to go from the gas phase, which is when we're discussing boiling point, we're discussing what energy, how much energy we need to put in to go from the liquid phase to the gas phase. We want to go here. So we need to break what is the intermolecular forces to do that phase change. So here forces are weak. These forces are stronger in dipole. So now what happens in butanol? Now in butanol, we have an additional force besides having the dipole and London dispersion forces, which is present in pretty much every molecule. We have another important interaction, which is hydrogen bonding. And when you learn intermolecular forces, you know here, this hydrogen is capable now to hydrogen bond. Let's say that I have another molecule of alcohol, right? And here you can have a network of hydrogen bonds and so on. And that's the strongest of these three intermolecular forces. So hydrogen bonding. Notice that here the molecules have the same number of carbons. Here we're adding a substituent, so that increases masses. As the mass, this is a higher molecular weight than that. However, this also has increased mass due to the substitution of one of the hydrogen by the OH. However, the most important factor here will be the intermolecular force. So if I need more to break this, I need more energy to put in and break those intermolecular forces. That means this molecule has the highest boiling point. So I'm just going to give them now a number, say molecule 1, molecule 2, molecule 3 is the butanol. So the highest boiling point will be in the molecule 3 that has hydrogen bonding, the strongest intermolecular force. Then we get molecule 2, which has dipole interactions. And lastly, the lowest boiling point would be butane. So now we need to remember that also for intermolecular forces, we want to consider mass. So say that you have larger molecules having larger mass, and also branching. So I'm going to give you another example with other structures. Let's say that we have, let me do that, that's butane. And I'm going to keep that. And again, remember that when we want to do a phase change, we need to break those intermolecular forces. So now here we have 4 carbons, and now let's think about another molecule that has also 4 carbons. Well, actually, that has 1 in the center and 4 more that has 5. So let's keep it consistent. I'm going to add 1 more. Now here, all we have is London dispersion forces. Also, sometimes we will see that as van der Waals, or simply dispersion. Now, when the molecule has a shape like that, molecules can get together in those fleeting dipoles that will help this molecule stick together in that sense. However, if we have a shape like that, they cannot get that close. So this has minimal London dispersion forces. So because it cannot associate the same way, we predict that this molecule will have lower boiling point than this, because here association is stronger. So we need to consider the structure. All here is the relationship between what is the molecular structure, what are the groups, if we have polar bonds or not, but structure and property relationship. That is, what is the structure of this molecule, and the property now that we're interested in is boiling point. The stronger those forces, the higher the boiling point.